Okay, uh, so good morning students. Once again, the last session we discussed about the working of the tunnel diodes. Okay, so today we will be focusing on some more two terminal devices. So the first device which we are going to discuss today is IR emitter. Well, in fact, a couple of sessions back we had discussed about the working principle of light emitting diodes. Okay, so frankly speaking, with respect to the principle of working, LEDs and IR emitters almost work in a similar fashion. The only difference is that LEDs emit the light which falls under visible light spectrum, whereas IR emitters, the wavelength of the light or the signal which is being emitted by them falls under infrared region. Okay, so that's the basic difference between LEDs and IR emitters. Okay, but still, let us just focus on some of the important points. Okay, fine. So infrared emitting diodes, well, IR stands for infrared emitting. So these are again semiconductor based solid state gallium arsenide devices. So you can observe that IR emitters, they are, the material itself is of gallium arsenide. Okay, hope you can recall some of the things which I had mentioned when we were talking about light emitting diodes. Okay, light emitting diodes, the material of which they are made up of is usually of direct band gap semiconductors. Okay, like silicon, germanium are indirect band gap semiconductors, so they are not good emitters of light. So instead of that, we normally go for compound semiconductors, especially a combination of gallium and arsenide. So the same thing can also be used here. Okay, same material, right? Just if you just fine tune the band gaps, you can get infrared light being emitted out of that particular diode. Okay, alright, so the point to be remembered here is IR emitters are usually made up of gallium arsenide material that emit a beam of radiant flux. Okay, radiant flux we usually denote it by the symbol psi. Okay, it is nothing but the strength of the light that is being emitted. Okay, if we talk it in terms of light, okay, luminosity, we call it as radiant flux when it is forward biased. So when the junction is forward biased, the electrons from N region combine with excess holes of the P material in a specially designed recombination region sandwiched between P and N type materials. Okay, so the principle is again the same, right? Let us just do it. Okay, if I consider this to be a region of N type, okay, and let me just consider one more region which is of P type, which is below it, so that's of P type. Okay, so now in principle it says that the recombination, okay, happens within this particular area. Okay, the junction space which is in between N and P type. Okay, so from here we get the IR rays, IR emitters. Okay, because the recombination process happens here. Okay, alright, so during the recombination process the energy is radiated away from the device in the form of photons. Yes, the generated photons are either reabsorbed in the structure or leave the surface of the device as a radiant energy. Alright, so the point is light is being emitted out of this particular PN junction. So that's the general structure of a semiconductor IR emitting diode. Okay, so you can very clearly observe the blue color region is of N type, the gray colored structure is of P type. Okay, and the recombination happens below this, within this N and P region, so that the IR rays are emitted outside. Okay, fine. See, you should be very careful when you are dealing with the devices wherein either input or the output parameter is light. Okay, in this case you will have to understand that in the case of LEDs and IR emitters, please understand that the input, okay, for these particular devices, the input is either current or voltage, V or I, right, and the output is light. Okay, so this light will be either in visible spectrum. So if it is in visible spectrum, then we call it as the device as LED. If it is in IR range, then we call it as IR emitter. Okay, as simple as that. But the point is, that's the output, okay, which we obtain, right? If the same thing is being reversed, wherein light will be input and the output will be either a current or a voltage, right, then we call such structures by some different names, right? We call them as photodiodes, okay, which we will be studying very soon. All right, so to talk further about IR emitting diode, well, that's a general structure and the construction. If you take a cross-sectional view, right, you can just observe that that's a more technical construction, wherein these gray colored structures are just supporting units, so they are reflecting parabolic surfaces which ensure that maximum IR rays are getting emitted. Okay, they are not lost. Okay, so it is just a nice closed chamber wherein IR rays will be emitted and they are taken out. Symbolically, how does a IR emitter look like? Okay, so that's the symbol of a IR emitter, which almost resembles that of an LED. Okay, fine. So the commercially available IR emitters, how do they look like? Okay, I have just taken some of the snapshots. How do they appear like? Okay, so these are all IR emitters. Okay, IR cables and all these things. Fine. See, practically where do we use them in the day-to-day life? Especially the remote controls which we use in the case of televisions. Okay, the remote control possesses IR emitter, right? Okay. Okay, so we will not be discussing on the strength of the light being emitted, because you need the basics of field strengths and also to some extent the antenna parabolic things and all. So we'll just ignore these things. Okay, but just to state a point, the first diagram is the typical radiant flux versus DC forward current for an IR emitting diode. Okay, wherein it is very clearly observed that there is a linear relationship, almost a linear relationship. And coming to the radiation intensity pattern of a IR emitting diode, you can just observe that it's some kind of a parabolic representation. Okay, you will be learning about these things. Okay, how to represent the radiation patterns whenever you take up a course on antennas, especially in your third year or maybe fourth year. Okay, so for now we'll just skip these things. Okay, so coming next is a photodiode. Okay, so in principle a photodiode is exactly the opposite of that of a LED or a IR emitter. Okay, as I just previously mentioned, in the case of a LED and a IR emitter, the input is a current or a voltage and the output is light energy, whereas in the case of a photodiode, the input is itself light, whereas the output is either a voltage or a current. Okay, so in principle it is exactly the opposite. But what about its construction and the working? Let us try to understand. Okay, a photodiode is a semiconductor PN junction device. So basically it's a semiconductor based PN junction device whose region of operation is limited to reverse bias. Well, something interesting. Okay, very interesting, right? So for a photodiode we are not using the forward bias region. Okay, although in principle, okay, to some extent forward bias region can be used, but however practically for more efficiency we usually go for reverse bias region. Okay, I'll tell you why. Then the second point, the reverse current which flows through a photodiode is due to the thermally generated minority carriers. Again, interesting point. Okay, there is no involvement of majority carriers here. We are talking more about minority carriers. Okay, now I think you can just correlate to some extent. Reverse bias, minority carriers. Okay, then so in the N and P type materials. All right, symbolically how do we represent a photodiode? Okay, well, the normal diode and with light as the input parameter, right? See, if the arrow was pointing outwards, then it would have been a LED. Okay, since the arrow is pointing inwards, that represents a photodiode because light is input here. It's an input parameter, photodiode. Okay, so you should be very careful in observing the direction of the arrows, okay, which represents the light energy. So here light is taken up as a input parameter. It is made to fall on the diode. Okay, and when we say light is being made to fall on the diode, we try to focus that light falls mainly in the reverse bias region. Okay, fine. So we'll talk about it in the next slide. But yes, the basic arrangement and the construction of a photodiode, how does it look like? Well, it's a simple PN junction diode, and that's the light energy which is being made to fall. And I think this is a lens. Okay, the lens, optical lens, which actually directs the light and ensures that it falls at this particular region. Okay, so what do we have here again? The light is focused so that it primarily falls again within the depletion region. Depletion region. Okay, so that's an important point. And another point to be focused is that just observe the biasing that is being done here. The P region is connected to the negative terminal of the battery and N region is connected to the positive terminal of the battery. What does that mean? That means we are trying to reverse bias the PN junction. So when we reverse bias the PN junction, what happens to its depletion region width? The depletion region width increases. So I'll just write a point here. Due to the reverse bias, the depletion region width increases. Okay, so when the depletion region width increases, all that we can say is that this particular width increases. So when this width increases, naturally more and more light can be made to fall within this depletion region. Okay, now there are two questions that arise. The first question is that why is it that the light is not made to fall in the P region or in the N region, and why are we trying to focus the light and then forcibly make it to fall within the depletion region? Okay, well, the first point is that the PN junction is reverse biased. The second point is that the carriers are thermally generated, okay, and they are minority carriers. Okay. So considering these 2 points, this P region, it consists of majority carriers. N region consists of electrons as the majority carriers. Okay. So we are trying to ignore the P region as well as N region. Then coming to the depletion region. Well, in the depletion region, in principle, without any application of external bias, there are no free carriers at all. Right? Then why are we trying to shine light within that depletion region when there are no carriers? Because this region is completely devoid of any free carriers. Devoid in the sense there are no free carriers. However, when light falls, what do we mean by light? We are trying to pass some energy, photonic energy within the depletion region. Right? So what does that mean? That means the light energy gets transferred to the crystal structure of the depletion region, due to which some of the crystal bonds break, and when they break, it results in the generation of minority carriers. Okay, and these minority carriers, since they are not affected by any reverse bias, they can very easily move. Okay, now this is a very, very important point. Maybe, okay, we'll try to understand it in a lot more detail based on the next slide. Okay, well, this makes the things very, very clear. Okay, fine. So first of all, the point is it is reverse biased. Reverse biased. Okay, so when it is reverse biased, just observe what has happened to the depletion region width. It has increased so much, right? Right. The purpose of reverse biasing the PN junction is to ensure that the depletion region width is as large as possible. And the purpose of ensuring that the depletion region is as large as possible is again to ensure that more and more space is available within the depletion region, so that more and more photonic energy can be made to fall. As simple as that. Okay, so now you can just observe there is so much space available within the depletion region, so that more number of photons can be made to fall. Okay, so what do we mean by more number of photons? More energy can be transferred, right? Okay, which means more energy, more photonic energy can be transferred to the crystal structure, so that more number of bonds will break. When more number of bonds will break, more number of carriers will be generated. Okay, now because it is reverse biased, now let us just focus. See, this region is of N type. Okay, and this is of P type. Now due to the applied external voltage, right, what will happen here? Within this region, there are electron and hole pairs getting generated. Okay, now how do they get generated? By the way, when light falls on them, there is a transfer of light energy to the crystal, due to which there is a, we say that there is a transfer of thermal energy, right? Okay, light to thermal. So due to that exchange of energy, thermally generated minority carriers appear. Why do we call them as minority carriers? Because due to the applied external bias, okay, the positive, just focus on this particular carrier, okay, it is positive. Due to the applied external bias, we are applying positive voltage to the N type. So it's quite obvious that a hole tries to move in this way. Similarly, an electron tries to move in this way due to the applied external bias. Okay, so it's electron and here it is holes which try to move. And do they move very freely? Yes, they move very freely. Why? Because they are minority carriers and they are absolutely not affected by the applied bias itself. If they were majority carriers, then they could not have crossed the junction at all. Okay. However, these are minority carriers and they can very easily move. Okay. So, this constitutes a current, but it is not forward current, it is reverse current. Although it is not what you can say, appreciable current as that of forward current, but still we get some reverse current out of a photodiode, which can be used for some meaningful applications. Okay. So, I hope this concept is clear for you students. 3 to 4 parameters are involved here. First one is that photodiodes work in reverse bias. The depletion region is made large so that more and more amount of light falls. So, there is a thermal generation of minority carriers, and these minority carriers are not affected by any of the depletion walls. They can very freely move and they get collected at the battery side. Okay, fine. So, where do we use them, by the way? Normally, see, these are the different varieties of photodiodes that are available commercially. Okay, different manufacturers, they manufacture it in a different way. Okay, the casings and all are different, but the point is here the application of light to the junction will result in a transfer of energy from the incident traveling light waves, that's the photons, to the atomic structure. Okay, this results in an increased number of minority carriers and increased level of reverse current. Then how does that current look like if I graphically plot it? Okay, let us just look. This is how the current through a photodiode looks like. I had just mentioned that it's not a forward current, it's a reverse current, right? Okay, so just observe. See, if it was a normal diode, you know that how a normal diode functions. In the forward bias, it is exponential current. In the reverse bias, there is a very, very small current, minute current, and then suddenly there is a surge of reverse current due to the breakdown. Okay. Now, if I just focus on this point, this is the reverse current before breakdown, which is extremely small, right? Okay. So, the same is being taken here. Initially, without application of any light energy, whatever small reverse current is flowing through a photodiode is called as dark current. Okay, it's very, very small. This current is without application of any light energy. Okay, and what about this region? I could have started here, right? But why is this current flowing from this voltage point? This is the forward bias knee voltage or the threshold voltage for a diode. So, obviously, the current has to start from this point, right? Okay. So, all right. Now, as the light energy increases, as the number of photons are increased, more and more minority carriers will be generated. That results in more and more current. Okay. So, if I just draw an arrow here, it means as light strength increases, more and more light strength increases, this results in more current. To be specific, it is reverse current. Okay, fine. So, that is exactly mentioned, and as an increase in the light intensity will result in a similar increase in the reverse current. Okay. So, what are the parameters here? It is I lambda. What does lambda mean? The current which is dependent on the wavelength of the photonic light. lambda. Okay, and just note the magnitude of the current, it is in microamperes. Okay, so these are the commercially available photodiodes. Fine. All right, so that was all about photodiodes. Then lastly, coming to its applications, where do we use them? Photodiodes are normally employed or used in alarm based security systems. Okay, this slide gives you a very simple example of an alarm system. Okay, so just observe, it's a light source which generates light, and light falls on this particular photodiode detector. Okay, now when somebody crosses here, okay, light is obstructed, right? So whenever light gets obstructed, there is no current flowing through a photodiode. So when there is no current flowing through a photodiode, okay, the sensor just activates and it gives a sound, okay, or an alarm, right? So these things we usually observe in the security systems, right? Airport security systems. So the same thing is also explained here, where photodiode can also be used in counting operations, okay, especially in airports and all, where the luggages are to be counted. There will be a conveyor belt which will be continuously rotating. On that particular conveyor belt, luggages will be kept, okay, and those luggages will be slowly moving, and on both the sides, at one place there will be a light source, and at the other place there will be a photodiode detector. So as the luggages they just move, they just cross the light section, the counts will be updated, okay, like 1, 2, 3, 4, in that way. Okay, fine. So these devices find many applications, especially in security systems. Okay, fine. Now let us focus on the next simple device, which is called as a photoconductive cell. Again, it's a very simple device, but it is slightly different from a photodiode. In a photodiode, there is a diode involved, whereas in a photoconductive cell, there is no semiconductor, there is no diode. Okay, however, we just have a simple semiconductor device, which is a two-terminal one. Okay, so in principle, a photoconductive cell is a two-terminal semiconductor device whose terminal resistance, please focus on this word, whose terminal resistance varies linearly with the intensity of the light. Okay, so again here input is light, output we are not bothered about the voltage or the current, we are bothered about the output as a variation in the resistance. Okay, so in simple words, it's a photoresistive device, okay, or a photoconductive cell. So how does the structure look like? Okay, so these are the two wired terminals. You have a ceramic base surrounding, and on top of the ceramic base there is a very thin coating of photoconductive material. Okay, so that's the photoconductive material, right? Now whenever light falls on it, this photoconductive material, which is usually made up of cadmium sulfide materials, they are very sensitive to light. Okay, so whenever light falls on it, they start conducting. Okay, they start conducting in the sense their conductivity will either increase or decrease, right? So when that happens, it is quite obvious that the associated resistance also keeps on changing. So that change in the resistance is being taken up and used for some specific applications. As simple as that. Okay, so the structure is very simple. What about the symbol? Okay, so just look at the symbol. It almost appears to be as if it is a variable resistor itself, but since it is a photoconductive cell, it's a variable resistor, then just surrounded by a circle. That's it. Okay, fine. So some important points. The photoconductive materials most frequently used are of cadmium sulfide and cadmium selenide. Okay. Then regarding their peak spectral response, their peak occurs at the wavelength of 5100 angstroms and 6150 angstrom. Well, you know, this is just for information's sake. You don't have to remember these things anyhow. Then the photoconductive cell does not have a junction like a photodiode. Okay, well, this is very important point. Okay, then a thin layer of material connected between the terminals is simply exposed to the incident light. Well, this is the same as the explanation that I had given previously. Now, as the illumination of the device increases in intensity, yes. So, if I consider this to be that photoconductive cell, where this is that photoconductive material, which is usually of cadmium sulfide or cadmium selenium, whatever. Okay, so whenever light falls, right, so this particular sensitive material conducts, right, and so that you can just take these two terminals, and whatever resistance change occurs here, that will be our output. Okay, so that's our output. So as the illumination of the device increases in intensity, the energy state of a large number of electrons in the structure will also increase because of the increased availability of photon packages, right. The result is an increase in number of relatively free electrons in the structure and a decrease in the terminal resistance. Okay. So just to talk about the sensitivity curve of a typical photoconductive device. Okay. So what does this graph state? It's a simple one. As the illumination increases, as the strength of the light increases, what is happening to the associated resistance? Since the conductivity increases, it's quite natural that the resistance is going on decreasing. Okay, fine. And by the way, it's in log scale. Okay, so that means the resistance is very rapidly decreasing. Then coming to the applications, okay, so they are used in variety of applications because of their simplicity. One of the application is that it's used in a voltage regulator. Okay, so you can just observe it. Okay, if you just Google it out in the internet, you will find n number of applications of a photoconductive cells. Okay, and just to remind, in your next year, okay, you will be having some small simple projects. Okay, so wherein you will be asked to design some simple circuits and all. So there you will be using at least one or two such devices. Either you may use a photodiode, or you may use a solar cell, or you may use a photoconductive cell, or a Schottky diode, or a tunnel diode, whatever. But the point is, whatever two terminal devices we are going to study here, at least some of them you will be definitely using them for your projects, 100%. Okay, so it makes sense for you to really understand the basic concepts behind them. Okay, all right. So I think we'll stop here. So just to summarize, I think we looked at three very simple devices today. The first one was IR emitter, then the second one was a photodiode, and the third one is a photoconductive cell. Okay, so in the next class we will be discussing about solar cells. Okay, all right. So any doubts, students?